Okay, so here's where we were last time. What we were talking about last time is this idea of diagonalizability, and just a quick sort of reminder, refresher on what the idea of diagonalizability is. We would like to talk about a matrix which, by way of a conjugation, can be turned into a diagonal matrix. That's sort of our first point of view. And then don't forget, of course, we made the realization that this matrix can be thought of as a change of basis matrix. Different point of view then. You can think of a matrix as being diagonalizable if by looking at it with respect to a different basis, the result is a diagonal matrix. Right, so that's another, I think, important point of view. Okay, so diagonalizability means that a conjugate of the matrix is diagonal. Likewise, it means it is a conjugation of a diagonal matrix. That's an easy little bit of algebra. This P matrix is defined like so. Its columns are a basis of eigenvectors, and that P matrix, by that construction, is a change of basis matrix. Okay, all right, so that's what we talked about last time. Okay, moving along. Is this possible? Can this always be done? Let's go back up here to our list, right? So is every matrix diagonalizable? Well, what it boils down to is, does there exist a basis of Rn consisting entirely of eigenvectors? If there is some basis of Rn consisting entirely of eigenvectors, then here you go. Make that the columns of your P matrix. That's your change of basis matrix. Conjugate by that, and per the algebra that we did last time, yep, the result is going to be diagonal. So diagonalizability boils down to this one question: is there a basis for Rn consisting exclusively of eigenvectors? Okay, now here's how the sort of arithmetic works out. Recall that for any given eigenvalue, we're going to find an eigenspace that has a dimension, namely the number of vectors in a basis for that eigenspace, namely what we casually refer to as how many eigenvectors do you find, right? So this is how many eigenvectors you find. For each eigenvalue, correspondingly there is how many eigenvectors do you find. Grand total then, the grand total number of eigenvectors that you find for all the eigenvalues. Well, if I want that to equal to n, in other words, if I want to have enough eigenvectors to possibly be able to have a basis for Rn, in order for that to work out, I need for all of these inequalities to be equalities. Right? And it's not hard to see, because this is always a less than or equal. Right? This is always a less than or equal. If any one of these inequalities is not an equality, right? If there's a what I like to call missing eigenvector for any eigenvalue, if for this eigenvalue, if the multiplicity is 3, but there's only 2 eigenvectors, disappointing situation like that. Anything for any eigenvalue, and it's just not going to add up to n, right? If this is, for example, like that, you will not get enough eigenvectors, and therefore it's not possible for the matrix to be diagonalizable. Okay, now there's another worry that we have to think about as well. Just because you find enough eigenvectors, let's assume all of these are equals, you have enough eigenvectors, who says they're independent? Right? Maybe, and this is kind of an obscure worry, I suppose, but maybe a basis for the one eigenspace, right, and a basis for the other eigenspace. Maybe when you take this independent list of vectors and that independent list of vectors, when you kind of put them all into the same bucket, I mean, maybe that larger list somehow is dependent. How do we know that's not going to happen? And that's, like I said, something we have to worry about, but the good news is it never happens, and that's this theorem here. If you take bases for the eigenspaces, throw them all into the same list to form a, hopefully, fingers crossed, basis for Rn, that will always be an independent list. Okay. Okay, so, our concern then, will we be able to make a basis? Well, it all comes down to, is the number of eigenvectors that we find equal to the number of eigenvectors that we need? In other words, we just need to know for each eigenvalue that there's no missing eigenvectors. Let's see an example. This is an example we did initially. This is our first example. The characteristic polynomial was this. Notice in this characteristic polynomial, for each factor, there are corresponding roots and multiplicities, right? That first factor, there's the root and the multiplicity. This next factor is a root and a multiplicity. Right, so we have a couple of eigenvalues. How many eigenvectors did we find for that eigenvalue? Well, we found one eigenvector, and that is equal to the multiplicity. So no missing eigenvectors for that first eigenvalue. For the second eigenvalue, how many eigenvectors did we find? Well, look back in the notes. We found one eigenvector. Again, equal to the multiplicity. So what we see here is for all of the eigenvalues, the number of eigenvectors we found is the maximum that it possibly could have been, so no missing eigenvectors, and therefore this matrix is diagonalizable. And of course, we already knew it was diagonalizable. We diagonalized it. Okay. All right. By contrast, remember this one. This harmless, deceptively weird matrix, harmless looking but deceptively weird matrix. Characteristic polynomial, eigenvalue and a multiplicity. Now what happened though, when we took this eigenvalue, how many eigenvectors did we actually find? Well, we found one. Right? We were hoping for two. The multiplicity was 2. We felt like we should find 2. But we only found 1. That's not equal. That's a letdown, right? There's a missing, in some sense, feels like a missing eigenvector. And this matrix, therefore, is not diagonalizable. It's a pretty neat conclusion, by the way. All we knew before this was that in our attempt to diagonalize it, we failed. Right? We were hoping to find a convenient list of eigenvectors from which we would then diagonalize, and we didn't find that, but who knows what else could have happened. Now we know the matrix is not diagonalizable. Okay. All right. Okay, so there's more to say about diagonalizability. In fact, here, let me flip over. Going back to this page, this is from last time, I think it was. We were talking about this kind of pseudo-analogy between row reductions, putting a matrix into reduced row echelon form, and how there's a kind of an analogy between that and diagonalization, putting a matrix into diagonal form. Really confusing lingo. Really unfortunate lingo. And one thing I didn't get to is this last row here. Row reduction. Is it always possible to achieve reduced row echelon form by way of row operations? And the answer is yes, always. You can always put a matrix into reduced row echelon form. No problem. Okay. We have now an answer to this analogous question looking at diagonalization. Can you always put a matrix into diagonal form by way of conjugations, aka change of bases, aka similarities? And the answer is, well, at the time we didn't know, and now we know the answer, though. The answer is no. Let me say not necessarily. So maybe. Sometimes yes, sometimes no, right? It's unfortunate. Okay. All right. So there's still a little bit more to say about diagonalization, and what do you do if the matrix is not diagonalizable? We'll talk about that in a few minutes, but first I want to go to an application, and these are just a couple of little quick and cute applications. The big application for diagonalizability It's going to come later in the course in Chapter 6. Again, we're going to use diagonalizability to solve a huge category of important differential equations, which is a pretty clear application. Anyway, we're not going to get to that for a while. So just to tide us over, here's a reasonable question. Suppose you want to raise a matrix to a high power. Now, why might you want to do this? We'll talk about examples in a couple of minutes. Nice punchline though. Diagonalizability helps. So let's look at this example here. Now, here's our familiar matrix. Recall we've done a lot with this matrix up to now. We found the eigenvalues, we found the eigenvectors. Therefore, we found how to diagonalize it. This is that diagonalization, right? Okay. So not only is D a conjugate of A, but it is also true that A is a conjugate of D just by moving the matrices around. Okay, so what? Well, look what happens then when you raise the matrix to a power. Let's take A and square it, for example. Here's A. So therefore, there's A times A, aka A squared. That sounded confusing. Here's A squared. Right. Now associativity kicks in, right? I can move these parentheses around however I like, and P times P inverse just cancels. Right? No, I'm not having to sort of commute. You can't commute matrices, right? But that's not necessary. The P and the P inverse are right next to each other, and they just cancel. So how convenient. Note that what we have then is, as a result, with only this remaining, we have that not only is A conjugate of D, but furthermore A squared is the exact same conjugate of D squared. And I'm going to leave it as an exercise for y'all to confirm this, but the exact same thing happens if you raise A to any power. Lots and lots of cancellations kind of in the middle. Okay, so what does this do for you? Why is this a win? Well, the reason that this is a win is that raising a diagonal matrix to a high power is easy. It's super easy, in fact, right? Because multiply a diagonal times a diagonal, and you just multiply the elements on the diagonal. That's easily confirmed, right? Just do an example, persuade yourself. So you want to raise some diagonal matrix, such as -1 and 4 on the diagonal. You want to raise that to an nth power? Okay, here you go. Nothing to it. Right? So if you find yourself, for whatever reason, wanting to raise some random matrix to a high power, diagonalize, do this trick, you'll find yourself simply needing to raise that diagonal to that same high power. And then, of course, after you raise the diagonal to a high power, then you still got to do the conjugation. Sure. Right? But ultimately then, relatively easy arithmetic. Okay. So, for example, you might think to yourself, you know what, I'll just let the computer handle it. Which, sure. Right? But suppose you wanted to raise a matrix to the power of some unimaginably large number. I know computers are really, really fast these days. So let's say, I want to raise a matrix to the power of 10 to the power of 200. Right? So forget about it. No computer, possibly. Right? In the lifetime of the universe, fastest computer ever conceived of could never do that. Right? But this trick does it very easily. So neat trick. Again, this is just intended to be, kind of tiding us over quick and easy applications. Note diagonalizability is the thing that makes this work, right? Being able to rewrite in diagonal form is the thing that makes it work together. Here's another neat application. By the way, first time I learned this, I was in graduate school. I don't know, I never took a class as an undergrad where this particular cute little application got brought up. But has to do with Fibonacci numbers. I think y'all have almost all, if not all, heard of Fibonacci numbers. Fibonacci numbers are defined by this little formula right here. Right? We start with 0 and 1. And the next number is always the sum of the two previous. So you add those up, to get that, et cetera, et cetera. Right? And I'm sure y'all have heard some or all possibly of the mysterious appearances of Fibonacci numbers in places that you wouldn't expect. The one I think is super weird is if you go to the grocery store and buy a pineapple, right? You know, pineapples have that kind of diagonal kind of pattern on them, right, of little sticky things. If you count the diagonal stripes down the pineapple going all the way around, it's always a Fibonacci number. Isn't that weird? Right? It's crazy. Anyway, and there's a bazillions of other similarly mysterious appearances of Fibonacci numbers. Okay, so now question, if you want to find the 7th Fibonacci number, fine, here it is. It's just a little arithmetic. If you want to find the 400th Fibonacci number, you probably wouldn't want to toss that into a computer, right? Why not? But again, suppose you want to know the 100 quadrillionth Fibonacci number for whatever reason. Or maybe just want to know how Fibonacci numbers behave as n gets large. Can we understand the large scale behavior of Fibonacci numbers? Then this recursion relation is not that helpful, right? And here's the trick. This solution I'm about to show you falls into a category of other kinds of problems that are solved by the same technique, which is we're going to solve problems by turning them into harder problems. You'd be surprised how often this helps to take an already hard problem and make it even harder. So rather than understand how to apply this recursion relation, let me instead ask the, again, seemingly harder, how do I apply this recursion relation? I'm not just adding numbers. Now I'm multiplying by a matrix, keeping track of vectors, seemingly harder work. Okay. Notice equivalent problem though, because all this equation says is fn plus 1 equals that, which is fn plus fn minus 1. And then the second line says fn equals fn. So the second line is kind of without substance. It's just a freebie. Okay, so this recursion relation defines the same sequence. Okay. Now, what that means is if I want to know, the nth Fibonacci number, by the way, here it is. If I want to know the nth Fibonacci number, all I have to do, that nth Fibonacci number, is realize that it's what you get when you take the first Fibonacci pair, 0, 1, and apply this recursion relation here. That turns it into the next Fibonacci pair, right? Just apply that relation n times. Innocent observation. If you apply this n times, you're going to turn f0, f1 into fn plus 1. Right? So here we are, wanting to raise a matrix to a high power, just like we did on the previous page. So we already know the answer to this question at this point, and now it's all details and shouting. Here's the, before we get down into those details, observe that this nth Fibonacci number that we're looking for, it's the bottom entry in the vector that we're computing. The vector we're computing being as we're looking at 1, 0 times, we're looking at the left column of that matrix raised to the high power. Right? So I just want to take this purple matrix and I want to find the bottom left entry of it. And now the details, and I'm gonna skip over a certain amount of the algebra. It's just a little bit of tedium. Y'all are fully armed to do this. If you take this matrix here and you diagonalize it, namely find the eigenvectors, find the eigenvalues, right? Conjugate accordingly, right? Then here's the eigenvalues. Oh, by the way, before I go on, this number G is sometimes called the golden ratio. Another number that appears more than by any rights it feels like it should, right? Sort of an oddly relevant number, 1 plus root 5 all over 2. weird, but anyway. So those are the eigenvalues. Here's the eigenvectors corresponding to those eigenvalues. As such, here's the diagonalization. Right? Notice the eigenvalues, g and negative 1 over g, appearing in that diagonalization. Note the eigenvectors appearing there, there, and there. Straight up diagonalization. I mean, for one thing, here you go. I mean, you can, if you want to compute the nth Fibonacci number, bottom left entry of this product. So you got to multiply this out. You know, it gets a little weirder to look at if you do, but you just got to multiply that and multiply this and look at the bottom left entry, and that's your nth Fibonacci number. Okay. Even more convenient, notice that when n is huge, and that's our scenario, right? I mean, the whole reason we started this little trick was because if I want to find the 100 trillionth Fibonacci number, then n is massive, and I just don't want to do that kind of arithmetic. If n is massive, this number here is approximately 0. Not exactly, but it's pretty close to 0. It's highly ignorable, right? I mean, that is a huge exponent, and that eigenvalue is clearly less than 1. So, I mean, that's going to go away. And so if you take this matrix with that additional convenient 0 there, multiply this out, then what you get is what we have here, and therefore that bottom left entry, and therefore extremely close approximation for the nth Fibonacci number is this super compact little formula. And a nice conclusion that you get from this is, again, this approximation, but notice this series here, this sequence, geometric. Right? What happens as n gets bigger and bigger and bigger and bigger and bigger and bigger? Well, the denominator is constant. It doesn't change at all. All that happens is we keep multiplying by g. So Fibonacci numbers have this feature that it's approximately a geometric sequence. So, neato. Okay. How we doing? Questions? Everybody good? Okay. All right, like I said. Okay, the next page example is not at all fleshed out, and this is, I just kind of want to point out that this structure can come up in other circumstances. So just imagine a scenario where you have some system that you're trying to keep track of. Maybe it's an engine you're designing, or some sort of a contraption that you're trying to keep track of, and it takes values in stages, right? So don't think of this as a continuous system. Think of it as a discrete system, such that, you know, at time equals 0, this is the state of it. And then we do something discrete, thus leading to the t equals 1 state of the system. And then we do something again that leads to the t equals 2 state. So numbers taking values in stages. Sometimes the relationship between a given state of the system and the next state of the system, sometimes that relationship might be as simple as a matrix. Now, it might, of course, not, but it also could be that the actual values that you're keeping track of, let's say xk and yk, xk might be I'm sorry, let me write this a little bit differently. This AK that you're looking at, this BK that you're looking at, this might be the XK that you're actually interested in minus some fixed constant. Maybe this BK that you're looking at here, that might be your YK that you're actually keeping track of, and then minus a different constant. Right? So you might need to take the things that you're interested in, you might need to finesse them a little bit to turn them into other variables that play nicer. Right? One way or the other, by manipulating things around, you might find yourself interested in things that relate to each other by way of a matrix. And if this happens, if the system that you're interested in, if you can do the algebra around such that you can relate these two numbers by a matrix, then here we are again. You can predict all of the behavior of the system simply by knowing the starting state of the system, and knowing how to raise a matrix to a high power, which is, of course, the same thing that we've been doing on all the previous pages. M to a high power, same trick. Okay. So anyway, exactly how that might come up, I mean, gosh, there's lots of different possibilities. Okay. So be on the lookout for things like that. Okay. Let me, this is a pretty good place to take a pause. Does anybody have any questions about any of this Fibonacci business, or anything like that? Everybody's good. Okay, so the remainder of section 5.5, by the way, if you haven't noticed, section 5.5 is really, really long. It's super long. We won't even finish it today. So it's another one of these 2.5 lecture sections. But I want to address this question of what if the matrix is not diagonalizable? And let me remind you, so the answer here is that no, it's not always diagonalizable, so it's disappointing. And so very naturally, okay, well, if it's not diagonalizable, then what do? Is there a almost as good to diagonalizability? Is there a consolation prize to a failed attempt at diagonalizing a matrix? And the answer is yes. There is this thing called Jordan canonical form. It is the consolation prize to diagonalizability. Every matrix can be put into Jordan canonical form. Now, note the use of the lingo here. Again, this very convenient and somewhat misleading language being put into a form, right? So again, what I mean by that is if you give me any matrix, I can interpret that matrix as representing a linear transformation, and I can simply find another basis to view that linear transformation with respect to the result of which will be Jordan form. Okay, so again, the lingo, we talk about putting the matrix into the form. Okay. All right. So let me go back over here to this page. I'm going to call this Jordan. Also, just to follow the grammatical structure, I call this Jordanization. It is always possible, right? By way of conjugation, aka change of basis, preserving the underlying linear transformation just like we were doing with diagonalizability. It's the same there, right? The only difference is that, again, this is a little bit of a disappointment. It's not as cool as diagonal form, the form itself, right? Diagonal form, by the way, let's take a moment to appreciate how nice diagonal form is. It's super simple to describe. All zeros except for on the diagonal. Right? I mean, super easy to talk about. Super easy to do things with because of the fact that it's all happening on the diagonal. And the diagonal, as you all know, is really important in how matrices multiply. So what we have to ask now is, what is this form? That we're talking about. So as we go through and I tell you what Jordan form is, just keep in mind that again it's the what you can do when diagonalization can't. Right? Keep in mind that what it represents is it's just a way of understanding the underlying linear transformation. The linear transformation is being preserved. It's still T, just in a different language. We're viewing it, that same T, by way of looking at it with respect to a different basis, right? So it's, in some sense, it's in the diagonalization kind of area. It's just, the disappointing consolation prize that you get when diagonalization doesn't work. Okay. Here's the bad news about Jordan form. It's really hard to describe. It's a weird set of rules. And let me point out before we get into that, so is row reduction. right? I mean, reduced row echelon form is a pretty strange little list of rules about increasing numbers of leading zeros and pivots and all the other entries in that column. A seemingly arbitrary list of rules. Now, eventually, we found, the reason that we like the reason we like reduced row echelon form is because it helps to understand solution sets. You can solve for your pivot variables in terms of your free variables. I mean, it's not immediately obvious from looking at these rules that it's going to help you understand solution sets. Right? We had to do some work to get to that. So analogously here, it's going to be a little bit of an uphill slog for me to tell you what the rules are here. But just keep in mind where this is going is this is going to be a weird though, and inconvenient though it is, it's a really convenient way to understand linear transformations that are not diagonalizable. And it is going to help us understand those linear transformations. And as with all the rest of the stuff that we're doing here in this section, it's gonna help us solve differential equations. Okay, enough of the preview. So let's get back to it. Here's the rules. Think of this as the kind of chapter 5 version of reduced row echelon form, right? It's a bunch of rules whose convenience will reveal itself later. Okay. All right. So, Jordan canonical form is made up out of what we call blocks. Blocks on the diagonal. Now, by on the diagonal, what I mean is that these corners of these blocks are strictly on the diagonal. Okay. All right. Let me put this back here because we have these blocks on the diagonal. And then, maybe some more, and how many, it depends on the situation. Outside of those blocks, all zeros. So when I say that Jordan canonical form is made up out of diagonal blocks, I mean that pretty literally, right? Everything outside of these diagonal blocks, strictly all zeros. Okay. All right. Now, what's inside of these blocks? Well, let's take a look at one of them. For example, let's look at this second one. This block. There's more to say about what's on the inside, but the couple of quickie observations I want to make now is that block, in a couple of pretty strong ways, corresponds to one of the factors of the characteristic polynomial. It's really hard to see this coming. It's really hard to prove why this is the case. This is well beyond what we can reasonably do in Math 216. It's just beyond the scope of the course. So this is a take on faith situation. I apologize for that. But it's the nature of the beast. So here's the connection, the relationship between the block and the factor is as follows. The diagonal entries on that block are the eigenvalue, aka the root corresponding to that factor. And the size, or you might say the dimension of that block, is the multiplicity in that factor, or the multiplicity of that eigenvalue. Again, mysterious and deep fact that's true for reasons that we're just not going to be able to talk about. So, sorry. Okay, but nevertheless, important to retain. So make sure to be aware of these two observations. Okay, now this leaves a lot of yet unaddressed, right? So I've told you what is outside of the blocks is all zeros, and I've told you exactly what's on the diagonal of the blocks, but I have not yet told you anything else about what's going on in here. There's a lot of sort of question mark of what else is inside of an eigenvalue block, and that's the next thing that we need to talk about. Before we go on though, one other quick thing I want to mention. The book does not use this term, eigenvalue block. to describe this thing that I like to call an eigenvalue block. In fact, the book doesn't give it a name at all. And I think that's super weird. It's a very natural and important thing to want to talk about. And the way we talk about things is to give them names, right? So I'm calling this an eigenvalue block. And again, you won't find that term in the book. Again, the reason I call it an eigenvalue block is because the diagonals are the eigenvalue. And the dimension is the multiplicity of the eigenvalue. So, strong connections to the eigenvalue, I think, make this a natural terminology. Let me pause for just a second if anybody has any questions. How we doing? Is everybody happy? Okay. All right. Okay, so what is inside of an eigenvalue block? Let me color code. So I'm going to use purple to represent an eigenvalue block. We're going to zoom in now, if you will. So kind of in the same way that, you know, like with molecules, what's inside of molecules? Well, atoms. Oh, yeah, well, what's inside of atoms? Well, protons and electrons and neutrons and all that stuff. And so we're going to be doing the same sort of thing here. I'm going to be talking about what's inside of this and then what's inside of that. Okay, so here's an eigenvalue block. What is inside of an eigenvalue block? And the answer is more blocks, which seems weird. More blocks also on the diagonal, namely with vertices on the diagonal. So there's blocks inside of blocks. Now remember, we already knew that we had, let's see, I'll do it like this, that outside of the eigenvalue blocks was all zeros. Now we see that there's more blocks on the inside. Well, outside of those inside blocks, also all zeros. So lots of zeros. Which, by the way, good news, right? We like zeros. Zeros are easy, right? Okay, so these blocks have a name as well. These are called basic Jordan blocks, or sometimes they just call them Jordan blocks. So that's what's inside of the eigenvalue blocks, is Jordan blocks and a bunch of zeros. Okay, are we okay on that? Any questions so far about that? And we're going to click up the power on the microscope again in just a moment. Okay. All right. Okay, eigenvalue blocks, inside of which are basic Jordan blocks. Inside of which now, so let's look at this, for example, basic Jordan block inside of an eigenvalue block, and inside of the basic Jordan block, good news, it's always the same. Always the same thing. There is a single number on the diagonal. By the way, we know what that number on the diagonal is if you think about it, right? So on the diagonal of a Jordan block, well, that on the diagonal of a Jordan block is also on the diagonal of the eigenvalue block, which, as we already know, are just the eigenvalue corresponding to that eigenvalue block. Right. What else is there inside of a basic Jordan block? Well, this is a little weird seeming, but there's a bunch of ones, always one, oddly, mysteriously, just one, exactly one, just above the diagonal, sort of one. They call it the super diagonal sometimes. I find that a little pretentious, right? So I'm just going to say just above the diagonal. Okay. And then zeros everywhere else. Okay, so notice all the zeros. Outside of the basic Jordan block, outside of the eigenvalue blocks, all zeros. Outside of the basic Jordan blocks, inside of those eigenvalue blocks, all zeros. Outside of these two thin strips, even inside of the basic Jordan blocks, all zeros. So lots and lots and lots and lots of zeros. And here's the good news. If you think about it then, so we've got these blocks that are on the diagonal, inside of which are smaller, thinner blocks on the diagonal, inside of which are pretty much almost only the diagonal, except for ever so little that's just barely off the diagonal. What we get is a matrix that's very close to diagonal. It's almost diagonal. And that kind of tracks, right? I mean, so our goal was to find a consolation prize to diagonalizability. We were hoping to get diagonal. So it's pretty good news that even though this isn't diagonal, it's really close to diagonal. So, good thing. All right. So, so this is called, these are the rules. So we're done, by the way. That's what Jordan form is. And just by way of a couple of examples here, let's look at, these. These are all in, Jordan form. Let me, sort of color in. So you'll notice here, this is an eigenvalue block, and this is an eigenvalue block. Notice it follows the rules, right? We've got all a single number on that diagonal. We've got all a single number on this diagonal. So the original matrix for which this is Jordan form, the eigenvalues are 3 and 5. Notice that as required in the rules, all zeros outside of the eigenvalue blocks. Now, inside of the eigenvalue blocks, basic Jordan blocks. There's a basic Jordan block. I know it's a basic Jordan block because it's just ones above the diagonal, eigenvalues on the diagonal, and all zeros everywhere else. Right? In the next one here, we have kind of a silly little basic Jordan block and another little basic Jordan block. Now let me spend a moment talking about this. I mean, can you do that? I mean, is a 1-by-1 matrix, is that actually a basic Jordan block? And let's think through the rules. Do all of the diagonal entries on this 1-by-1 matrix have the same value? Well, yeah, all one of them. So, yeah, I mean, sort of vacuously, right? There is that, though. Okay, here's the next question. This 1-by-1 candidate basic Jordan block matrix, is it true that all of the entries just above the diagonal are 1? Well, there are no entries just above the diagonal. So again, vacuously, I mean, due to lack of counterexamples, right? Yes. All of the entries just above the diagonal, there aren't any, are indeed 1, so no problem, so fine. And again, what about all the other entries? Again, there are no other entries. Are all the other entries 0? Why, yes they are. Again, vacuously. Okay? So, basic Jordan blocks can be 1-by-1, perfectly fine. That's how this example works. We have eigenvalue blocks, inside of which are basic Jordan blocks, inside of which are what they're supposed to be. Next example, and let me be quick about these. There's an eigenvalue block. Here's another eigenvalue block. Right? Diagonal entries and all that. Here's a basic Jordan block. Here's a basic Jordan block. Satisfies all the rules. Consistent diagonal entries. One's just above the diagonal. Zeros everywhere else. It's all good. Right? Likewise here. Basic Jordan block. So this is in Jordan canonical form. Everybody good so far? Do be careful with the basic Jordan blocks. It is tempting, for example, with this eigenvalue block, to think, well, why don't we, can I just call that, for example, a basic Jordan block? And, well, I mean, at a glance, it looks like, it is technically it satisfies all the rules, but then notice you're kind of out of luck on your ability to then follow the rest of the rules. Like, I guess you'd have to say this and this, right? But then, do you have all zeros outside of the basic Jordan blocks? No, you have that one there, and you simply cannot make that work. Right? So you where the ones are sort of tells you what you have to, where you have to kind of extend, if you will, the basic Jordan block. You've got to extend the basic Jordan block to include all the ones. Right? And you can't extend the basic Jordan block too far to include something other than ones just above the diagonal. So there's only going to be a single way to draw these blocks. Okay. All right, likewise for the next one. And let's see here. Again, I'll be quick. Eigenvalue block. Eigenvalue block. Basic Jordan blocks. All the rules satisfied. There you go. Jordan canonical form. How are we doing? Questions? Anybody? Yes?
Are all of these matrices the same, or Jordan form for the same matrix?
That is a fantastic question. And let me see here. No, they are not. And exactly how I know that, I'm invoking some rules that I have not told you yet. So there are some rules about that. And it's not a very short and simple answer, so I'm going to deliberately not answer your question but your answer will come on Monday. Yeah, yes.
Can a matrix have more than one Jordan form, or is it like reduced to echelon form where there's just...
Another great question, and the answer is it's complicated. Kinda, sorta, but not really, but in a way, kinda. So let me flesh that out next. It's a long discussion. It's about a 20-minute discussion, and so I'm going to wait until Monday for that. Okay, let's see here. How are we doing on time? Yeah, okay, so let's see here. So a quick summary then of what we have. So recall, we're talking about the consolation prize to diagonalizability. So we were conjugating, right? You can think of the conjugation either way. We were conjugating, hoping to turn our matrix into a diagonal form. Didn't work out. Oh well, we don't get diagonal form. Okay, I guess I have to deal with the disappointment of merely having almost diagonal, namely Jordan form. And so we have, again, two equations. You can think of Jordan form as being a conjugate of the original matrix. You can think of the original matrix as being a conjugate of its Jordan form. Those are really the same equation, just kind of a little algebraic shuffle. Again, what we're talking about with a conjugation is a change of basis a certain way. Now here's another little bit of terminology that the book does not give a name to. I think that's, again, limiting, very limiting. So I'm going to give a name, the basis. That is the basis with respect to which we view the transformation to get into Jordan form. Or said differently, the basis whose columns make up the change of basis matrix. I'm going to call it the Jordan basis. And I shouldn't say the, I'm going to call it a Jordan basis. It's not unique. Turns out there's lots of them. But nevertheless, we're going to need to refer to, when is a basis a Jordan basis and when is it not a Jordan basis. So it's the way you talk about things is to have names for them, so I'm giving this a name even though the book didn't. Extra little bit of terminology. One last thing, real quick, I want to call your attention to the fact that what I've written down here might look familiar. So let me compare y'all may recall a ways back we were talking about, this was our summary for diagonalization, and when a matrix is diagonalizable, some are, some aren't, right? This is the conjugate of that, that's a conjugate of this. This matrix is a change of basis matrix, and there's something special about the basis. And well, likewise with Jordan form. Now, all matrices are Jordanizable, all of them, no exceptions, right? It's the same, this is a conjugate of that, and that's a conjugate of this, and again, it's the same, that the matrix by which you're conjugating represents a change of basis, and it's a change of basis involving a new special basis. So, what's nice about the diagonalization matrix is that it's a basis of eigenvectors. For Jordanizing, it's not. It's a next best thing called a Jordan basis. Okay, questions real quick. Anybody have any? Yes?
Are diagonal matrices a eigenvalue matrix?
Yeah, in fact, that's right. So it's a great question. So let's just kind of think that through real quick. If you have a diagonal matrix, what you've got is on that diagonal, you've got a bunch of itty-bitty, teeny-weeny basic Jordan blocks that are 1 by 1. And yeah, so it's fine, right? Great question. Anybody else? Okay, good stopping point. See y'all later. Have a good day.